I know what you're thinking of. If you see something like this, you will tell me that this limit does not exist. Are you really sure about that? Let's go to the board and see together. To understand what happens when n becomes very large, we need to find a better approximation of the argument of the sine. The first step is to factor out 4 n squared from inside the square root. This gives 2 pi n multiplied by the square root of 1 plus 1 over 2n plus little of 1 over n. Little of 1 over n simply means a quantity goes to 0 much faster than 1 over n as n becomes large. Now we use the Maclaurin expansion of the square root. We know that the square root of 1 plus x is 1 plus x over 2 plus little o of x. Applying this formula, our expression becomes 2 pi n multiplied by 1 plus 1 over 4n plus little o of 1 over n. Now we multiply everything out, so the whole expression simplifies to 2 pi n plus pi over 2 plus little o of 1. Now we substitute this expression back into the sine. We obtain the sine of 2 pi n plus pi over 2 plus little o of 1. At this point, we use a very important property of the sine function. Sine is 2 pi periodic, which means that adding an integer multiple of 2 pi does not change its value. In other words, the sine of 2 pi n plus alpha is exactly the same as the sine of alpha. In our case, alpha is pi over 2 plus little o of 1. So our expression becomes simply the sine of pi over 2 plus little o of 1. Finally, we take the limit operation as n goes to infinity. The little o of one term goes to 0, and because the sine function is continuous, we are simply left with the sine of pi over 2, which is 1. And this is the value of our limit. And this is the whole trick. The dominant term, 2 pi n, is exactly an integer multiple of the period of the sine function, so it has absolutely no effect on the limit. The only part that survives is the constant offset, pi over 2, and that alone determines the final answer.